Hi, this is the second part of 5.1, the polynomial functions. The first part we talked about the power functions, and on this one it's just the actual graphs and coming up with the equation based on the characteristics. So I decided to go ahead and give you the definition like we did in class. Polynomial function is of the form f of x equals a sub n x to the n plus a sub 1 n minus 1 all the way out to a sub 0, where a sub 0 out to a sub n are just real numbers such that a sub n does not equal 0. And we spent a little bit of time with that in class, and I'm not going to go back into detail what to do with the the subscripts on these terms. So just go back to your class notes for that. I'm going to just concentrate on just the basic information here. So example 1, create a polynomial function with the following characteristics. Okay, we want the x-intercepts to be 2, -3, and 5. Now, something that we learned in class, that if you know that an x-intercept, let's say the x-intercept is c, some number c, then there's a factor based on that. It's called x minus c. So for example, if you know 7 is a factor, 7 is an x-intercept, crosses the x-axis at 7, then the polynomial function will have x minus 7 as a factor. So if c is an x-intercept, then x minus c is a factor based on that. It's actually called the factor theorem if you want to know, but that's another subject. So so the x-intercepts are 2, -3, and 5. So what you would do, since if 2 is an x-intercept, then x minus 2 is a factor. If -3 is an x-intercept, x plus 3 is a factor. If 5 is an x-intercept, then x minus 5 is a factor. But there's one little bit of information that they put down. They say, well, 5 has multiplicity too. And what that basically means is 5 is not only an x-intercept once, it actually has an x-intercept there twice. Basically, what that basically means is the degree is 2, which means there are 2 x-intercepts at the same location, which kind of doesn't really make sense. But what it is, the graph just comes in and then comes back up. So what we call that is bouncing. So book what we use the terminology, it hits the x-intercepts and turns the other direction. I'm pretty laid back. I just call it bounce. It just hits and comes back up. It bounces. And so what I'll do is I'll put a degree 2. These other ones here are degree 1 because there was no multiplicity other than 1 on those. Okay, and a little bit later we're going to be talking about something called COBE, and COBE is a little acronym that I kind of created myself, and it stands for crossing when it's odd, bouncing when it's even. And since Kobe Bryant is a basketball player, most people know who he is. It's an easy way to remember. I used to spell it with K, but people always told me Kobe, a crossing is with a C, not a K, and I know that. But Kobe is not spelled with a C either. Kobe Bryant is anyway, so I can't win, on that one. But it's a way to remember which one it does. So the graph actually will cross the x-intercept and go in the other, underneath it or above it, depending on which way it's coming in the first place. It goes through the point when it's odd, and it bounces when it's even degree. So if you were actually going to do this, when the x-intercept here would be 2, so the graph crosses that point, and bounces at that point. So, and on this one, we're going to do that. We're going to actually do a sketch a graph based on what I just told you on example 1. But these have different x-intercepts. And so 2x squared, x minus 1 to the first, x plus 4. So the x-intercepts are going to be at -4, 1, and 0. The 1 because it's x minus 1. -4 because it's x plus 4. -4 makes that 0. And 2x squared is 0. Now you're like, well, what about the 2? Well, 2 doesn't provide any x-intercepts. The x squared does, but not the 2. So the 2 is acting as a stretch, just like we did back in the transformations. So if that number was a 3, it still wouldn't have affected these x-intercepts. If this was a -5, it still would not have affected these x-intercepts. They still would have been in the same place. It's just the stretch or whether it's up or down, that depends on that number. So these are the x-intercepts. Now, I look at the Kobe thing, and I remember that, well, it crosses when it's odd, bounces when it's even. So the x squared has an even degree, so it bounces on this one, and it crosses on these two right here. Alrighty. So now I look at the graph and I say, I got to do the graph. Now we do in class, I show you in class different ways to do this. Some people choose one method over another. Some people will just plot a bunch of additional points. And I'm fairly lazy and I'm pretty laid back, like I said. And so I like doing it the easiest way I can. And so what I do is I look at what this thing looks like as far as this power function, which is what we talked about in the early part of 5.1. And that's going to be 2x to the fourth. Y equals 2x to the fourth. Now, why 2x to the fourth? Because the leading coefficient is 2, and there are 4 factors of x. So at the extremes, what we call the end behavior, the graph will look like y equals 2x to the fourth. You're like, well, what does y equals 2x to the fourth look like? Well, if you remember back in the earlier section, 2x to the fourth has this shape right here. So the left and the right extremes go up. And that's what's going to happen on the polynomial itself. So at -4, it's going to go up. At 2, it's going to go up. At the 1, it's going to go up from this one right here. So how these go up is like these go up right here. Now, the rest of the graph is based on Kobe. Okay? It crosses, it bounces, and it goes back there again. So if you got the graph going through a point and it's crossing when it should bounce, then you know you made a mistake somewhere down the line. But this is the shape of the graph, and that's all we really care about. We don't really care about how low these things go in this course. We just try and draw the generic shape. That's why I don't put any scaling on the y-axis. On your homework, you're going to see some graphs because the graphs will have that part of it. But I don't really care about what this is. So it's not scaled at all. So I will probably tell you this graph, right, part of the graph goes lower than this part simply because the gap between the -4 and 0 is wider than the gap between the 0 and 1, which allows the graph to go dip a little lower than possibly this. Does it actually? I'm not positive about that, but it's more likely that's what's going to happen. But again, I don't really care about how low you drop this off. So you might look, your graph may look like this. Somebody else's graph might look like this. And if you notice that person's graph, even though their graph dips down lower than yours does, they both have the same generic shape. And so you'd both be correct there. So we don't have a problem with that here. So, all right. Now, example 3, all righty, same situation. This one's going to have actually 4 x-intercepts, one at 0, one at -2, one at 4, and one at 1. And let's look at the Kobe part of this. The x plus 2 squared, so the -2 is going to bounce. But the rest of them has an odd degree. So they're going to cross everywhere else. And now I just have to look at the power function that it resembles. Well, what do you think? It's got a -3 in the front, but how many factors of x do you have total? Well, there's 1, 2, 3, 4, 5. There's -3x to the 5th. So we have to graph y equals -3x to the 5th to see what it looks like at the ends. And back in 5.1, earlier part of 5.1, we graphed these kind of problems, and it looks like this. We also did this in 3.5 when we did transformations as well. So y equals -3x to the 5th, and it's negative, we'll flip it upside down. So this graph right here that I've got here, it's going to have that same generic shape. So from this last x-intercept, it's going to go up, and from this last x-intercept on this, it's going to go down. And then everything else should go how Kobe does. So it bounces here, crosses, and then crosses to go back down. So sure enough, that's exactly what it looks like. But again, these little peaks and valleys, how high and how low they go, don't care. So that's not important in this situation with what we're doing. But that's pretty much it. That's pretty much it. And like I said earlier, though, I said, some people will do this by plotting points. They'll put -3 in there, and they'll see if it's positive or negative, and they will find out that it's positive. So they'll just plot points in between the x-intercepts. And if you plot a number over here, it's going to give you a number up here, so they put a point up there. They put a test number between 0 and -2 and 0, and they'll find its point up here somewhere. And they'll test between 0 and 1, which is not going to be nice, but they'll find out that it's negative. A lot of places to make a mistake, but it's safer, and if you do it that way, you don't have to remember Kobe. So if you just do a bunch of test points to me are dangerous, because if you use test points, what that basically does is if you make a mistake on one, your whole graph becomes problematic there. So and you got a lot of test points too. So that's why I like Kobe. Kobe, if I know what the general shape of the ends are, and then when they cross or they bounce at the x-intercepts, it's a whole lot safer and a whole lot easier and a whole lot cleaner to do. But remember, we don't care about the scaling. And that's it.